Welcome to this revision video on the binomial distribution. The binomial distribution is a discrete distribution which deals with a random variable. It is worth noting there are four main key points to a binomial distribution. You must have a fixed number of trials, so say you lob a coin 10 times. Each trial must be success or failure, so you either have with a coin heads or tails, nothing else. Two outcomes, success or failure. All the trials must be independent of one another, and the probability of success must also be constant. So say if you had your coin, an unbiased coin, probability of a heads or tails would be 0.5 throughout the experiment. For working out how many times you expect your random variable to occur, we use the formula of n, where n represents the number of trials, x is our random variable, and p is probability. So we do n combination of the random variable times the probability to the power of x times 1 minus the probability to the power n minus x. And this idea for the number of ways of arranging the random variable comes from this formula here, where if we had n objects with a of one type and n minus a of another, we could arrange it using this formula, n factorial over a factorial times n minus a factorial, to give us the total amount of ways of arranging the object in question. And if you wanted to work out probability of x being less than your random variable, less than or equal to, then you must use the tables, which I will go through in a couple of examples. It's also worth noting that the mean of a binomial distribution is equal to the number of trials times your probability, and the variance of the distribution is equal to the mean times 1 minus the probability. So, first example, 8 fair coins are tossed and the total number of heads shown is recorded. Find the probability of no heads, at least 2 heads, and more heads than tails. So first things first, define our random variable. Let's say x is equal to the number of heads. Could equally use tails, it doesn't really matter in this question, as we're told 8 fair coins, so the probability of a head and tail should be a half either way. So write out our distribution. The number of heads is binomially distributed with 8 trials, we're told, and the probability being a half, as remember we're dealing with a fair coin. So part A, the probability of no heads, well, we can write that as x is equal to 0. And if you're familiar with probability, you should know we can just do a half to the power of 8, because it's a half times a half times a half, so on, 8 times, and that should give us 0.0039. You could use the formula, just so you know, the formula stated earlier in the video. So that would be simply 8 in combination with 0 times the probability 0.5 times 0 times 0.5 to the power of 8. However, that equals to 1, and anything to the power of 0 equals 1. So in this instance we didn't need the formula, but for future reference you could use it. Part B, at least 2 heads, so we want the probability of x to be greater than or equal to 2, and all the probabilities add up to 1, and our table uses values probability of x being less than or equal to our random variable. So the best way to solve this would be to do the 1 minus the probability of x being less than or equal to 1. Work that out from our table. We have 8 as our n value and 0.5 as our probability. and our random variable 1, the answer is 1 minus 0.0352, which is equal to 0.9648. So just to clarify, what I've done here, if we draw out a number 9, we wanted the probability of x being greater than or equal to 2. And remember, we're dealing with discrete data here. So that's the same as saying 1 minus the probability of x being less than or equal to 1. Okay? Part C, we want to work out the probability of more heads than tails. So we've thrown the coin 8 times. So in order to have more heads than tails, we need to have at least 5 heads. So we can say the probability of x being greater than or equal to 5. Use the same principle in part B. We could do 1 minus the probability of our random variable being less than or equal to 4. Find that on the tables. There it is, 0.6367. And if you work that out, you'll find it comes to 0.3633. So example number 2, we're told the random variable x is binomially distributed with a probability of 0.4 with 50 trials. Find the largest value of k such that the probability of x being less than or equal to k is less than 0.05, and the smallest value of r such that the probability of x being greater than r is less than 0.01. Now I've chosen this question because I think it's quite important to understand how to solve these sort of problems, and it gives you a better understanding of the binomial distribution itself. So part A is quite straightforward. We want the largest value of k such that this equation is true, that the probability of x being less than equal to k is less than 0.05. So what value goes in here? Well, if we look at our tables, we can see, remember, we're dealing with n equals 50, probability equals 0.4, and the tables give us values for the probability of x being less than or equal to x. Okay, so if we look on our table, we want the probability less than 0.05, but the largest value possible. So 0.4, let's go down, 0.05 is here. So the largest value would be 13. Okay, we can see the probability of x being less than or equal to 13 on our table is 0.0280, and the probability of x being less than or equal to 14 is 0.0540. So this is the largest value below 0.05. Therefore we can say k must be equal to 13. So for part B now, we want to work out the value of r such that the probability of x being greater than r is less than 0.01. So remember, we want to get the question in this format here in order to use our tables to solve. So what we can do, before I show you how to solve this, just give you a quick bit of background knowledge. Remember, we know the probability of x being greater than some number, say 5, is equal to 1 minus the probability of x being less than or equal to 5. Okay? You should know that from the first example. So we can use that to solve this algebraically. We can say the probability of x being greater than r is just the same as the probability of 1 minus the probability of x being less than or equal to r. All I'm doing is the same thing as over here. And if you rearrange that, you get the probability of x being less than or equal to r being greater than 0.99. So we want the smallest value that can go in here that's greater than 0.99. So if we check our tables, we go down 0.99, you'll find that we want our R value. The table gives us the probability of X being less than or equal to 28. On our tables is 0.9924. So that would be the smallest value that's greater than 0.99. Therefore, R must be equal to 28.